Hi, I'm Dr. Incognito. In this video, we'll start with the geometric power series and create a power series representation for a logarithm using integration. So we begin with the power series representation of the function 1 over 1 minus x. This is equal to the simple geometric series summation n equals 0 to infinity of x to the n. And this is valid as long as the absolute value of x is less than 1. I'm interested in the following modification, 1 over 1 plus x, which can be written as 1 over 1 minus negative x, is equal to, by substitution, the summation of negative x to the n, replacing x with negative x in the formula above. So this is equal to the summation n equals 0 to infinity of negative 1 to the n times x to the n. And the interval of convergence is unchanged. So now we will integrate this function. The integral of 1 over 1 plus x dx. If you like, you can do a u substitution. U equals 1 plus x, du equals dx, and write this as the integral of 1 over u du, the antiderivative being the logarithm, the natural logarithm of the absolute value of u plus c. And so the integral of 1 over 1 plus x would be the natural log of the absolute value of 1 plus x plus c. So what this means is that we have a power series representation for the log of 1 plus x plus c. If you integrate the power series for 1 over 1 plus x, which was here, summation negative 1 to the n, x to the n. If we integrate that power series, then that will give us a power series expansion for the logarithm function that we see here. So the way we integrate a power series is term by term. We can integrate the power series term by term, which means that we can bring the integral sign inside of the summation. So this integral is equal to the summation n equals 0 to infinity of the integral of negative 1 to the n times x to the n dx. And this integral is easy to evaluate. Negative 1 to the n is a constant as far as x is concerned. And the integral of x to the n, that's a power function. The antiderivative is x to the n plus 1 over n plus 1. Summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1, over n plus 1. So there we have the power series representation for the logarithm. Let's write that down. So we have the log of the absolute value of 1 plus x plus c is equal to the summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. And when you integrate a power series, the interval of convergence is essentially unchanged. So the interval of convergence will still be the absolute value of x less than 1. Actually, there will be a slight improvement that we will investigate in just a moment. But first, let's clean up this left side a little bit. Since this is a specific function on both sides, maybe we can figure out the value of c. If we let x equal 1, we want this to be 1, let x equal 0, then we get the log of 1 plus c is equal to, if we let x equal 0 in the summation, then that would simply be the summation n equals 0 to infinity, negative 1 to the n, 0 to the n plus 1, n starts at 0, so we start at 0 to the 1, over n plus 1, that's the summation of 0. So that's 0. And the log of 1 is 0. So 0 plus c is equal to 0. That means that c is 0. And since the absolute value of x is less than 1, that means that x is between minus 1, and that means that 1 plus x is at least 0 and less than 2. So we don't need absolute values around the 1 plus x in this formula either. The c is 0, and the absolute values can be dropped, and we get a nicer form. We get the log of 1 plus x is equal to the summation n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. And now about that interval of convergence. The interval of convergence, we said a moment ago, was x between minus 1 and 1. But actually, in this series, both sides are valid if x is equal to 1, and so the equality is maintained. If we let x equal 1, then on the left side, we simply get the logarithm of 2, the natural log of 2. And on the right side, the summation n equals 0 to infinity of negative 1 to the n times 1 over n plus 1. And if we write out the first few terms of this series, we'll see that this is a familiar series. This is going to be, when n is 0, 1 times 1 is 1. When n is 1, we get a minus here and a 1/2. When n is 2, we get a plus and a 1/3. And you can see the alternating harmonic series here. Minus 1/4 plus 1/5. So this is the alternating harmonic series. And this converges. Now we actually know what it converges to. It equals the natural log of 2. That's the value of the alternating harmonic series. So the interval of convergence of the power series is actually x bigger than negative 1, less than or equal to 1. When x equals negative 1, then we have issues here with the log of 0 being undefined.